Good afternoon, everybody. Today's demonstration is on Ohm's law. In Ohm's law, E equals IR, where E is the battery voltage, I is the current, R is the resistance. We're going to start Ohm's law with this red brown resistor. That's the resistor color code. So now I have the power supply on. You'll see a graph of voltage on the vertical axis, current on the horizontal axis. So now I will increase the voltage and start collecting the data. So I'll just take some voltage values, keep the voltage values. So you can see here we're getting a nice straight line pattern. Okay, now I'm going to reverse the leads in the power supply to the resistor. And now I'll increase the voltage again on the power supply. You can see here now we have a negative voltage and a negative current. Okay, here you see a nice straight line pattern in this current voltage graph. So we got voltage versus current in this graph. Now I will highlight all the data and get this linear fit. In this you see we have a resistance fit of 230.6 volts per amp as the slope of that line. If you look at the equation E equals I times R, the R, the resistance, is the slope of that line, so we can conclude that the resistance of this resistor is that slope of 230.6 ohms. So this is Ohm's law. We have this nice linear relationship. This is an ohmic device. The next device I'm going to demonstrate is this diode. This is a very important electronical device for modern electronics. Okay, now the diode is hooked up in place of that. Okay, now I'm going to close off this graph, re-zero the sensors. That takes just a moment. Restart the collection with the diode, and we will erase and continue. So now I turn on the power supply, and I will check which way we are at. Okay, so now I will keep this point, and now we increase the voltage, and you can see we are starting to go up very steep, and the current is very, very small. You can see on the data table is to the left. I don't know if you can see it in the video. Okay, now I will turn on the power supply and switch the leads. And you can see here we have this point here. I'll just keep that and start increasing the voltage in the negative direction. So now I am off the graph. I'll have to change my axis in just a moment. Let me see if I can get... Okay, I'll keep that point. I'm going to change this scale right here to let's say -2. Right now you can see that point I had been missing a moment ago. Okay, now let me increase the voltage a little more negative. Keep that point. And keep. Okay, now I'll go a little bigger at the voltage. Keep that point. Keep that point. I'm getting some significant amperage. So you can see here, I have to turn that down, I don't want to burn this out. So I will change the scale back to -1, and you can see here this graph has a very sharp corner. So you can see that this diode would not predict Ohm's law. The resistor that we did earlier obeyed Ohm's law. It was a nice straight line. But here we have very different behavior. If I took a curve fit here, I have a small slope of only 0.2226. I could say I have approximately 0.2226 ohms of resistance in this regime of the diode. And then over here, if I try to take the slope of this section, it's a very steep slope of 27,360 ohms, so we'd have a very high resistance. Why is this so important in today's electronics? The location where we had the high negative current and the large negative voltage, this known as forward bias. In computers, that would be a 1 in the binary language. That means you're on. In the other direction, that would be reverse bias over here, where we were doing the positives on this reading. And you have such a very tiny, it would be a very tiny reverse saturation current in the reverse bias. The resistance is extremely large. That would be called a 0 in the computer, and that would be off. So that's how we get the ones and zeros in modern electronics. The diode is of course incorporated into the transistors, and computers have a lot of transistors in them. So then you get the ones and zeros, and you get your computer language and computer programming.